The next speaker is André Monteiro. André Monteiro is a civil engineer researcher in the National Laboratory of Civil Engineering in Portugal since 2005. He has a PhD on concrete durability and a vast consulting experience on inspection and repair of concrete structures. This presentation is about the recasting method or the cast-in-place method. André, as soon as possible, can you please start your presentation? Thank you.
Hello, good afternoon. Okay, I will present now the cast-in-place repair methods, which corresponds to the chapter 9 of the FIB Bulletin. In this presentation, I will start with a brief description of the cast-in-place repair methods. I will point out its main advantages and disadvantages compared to other repair methods. Then it will be highlighted the main challenges involved in the design. I will address the most common techniques for preparing the substrates and for placing the repair material into the forms. And finally, I will present some conclusions. The cast-in-place repair method consists of replacing the faulty concrete in the structures with new concrete or mortar with the help of formwork. It is a very versatile method that can be used in all sorts of surfaces, such as vertical, horizontal, and overhead surfaces. It can also be used in full depth and underwater repairs. The option for this type of repair lies, of course, in its advantages compared to other repair methods, such as the hand-applied mortar and sprayed concrete. Without any particular order of preference, we can say that the main advantages of these methods are that there are no particular limitations for the maximum depth of the repair, unlike other methods where above a certain depth it is necessary to apply multiple layers of material. It is easier to reproduce geometries with edged shapes due to the help of the forms. This method also supports a wide range of repair materials and placement techniques that can be adapted to different repair conditions, as we will further discuss. Also, the formwork offers several benefits, such as it prevents sagging and dropouts of repair material. It protects the repair material against early age drying, as well as against physical impacts during its fresh state. It guarantees a more uniform surface finish. Usually it does not require the application of a finish coat, as it is often the case when sprayed concrete is used. It also allows to perform full depth and underwater repairs, as already mentioned. As main disadvantages, it needs formwork, which makes this method more laborious, especially in overhead repairs. It is more difficult to reproduce curved geometries compared, for example, with sprayed concrete. There is a risk of segregation associated with the flow of the repair material through narrow spaces, such as between congested bars, although it can be overcome with the proper selection of materials and placement technique. And finally, it is difficult to use bonding agents, since they usually have to be applied before the fixation of the formwork and need to remain fresh until the time of pouring the repair material. However, bonding agents are usually not needed, provided that a good preparation of the substrate is achieved. Such as in the case of new construction, the design of the repair should satisfy both the structural and the durability requirements of the structure. However, it can offer particular challenges compared to the design of new structures. One of these challenges is that the repair usually involves a structural intervention in an already loaded structure. In that regard, the designer should avoid the transfer of loads from the concrete to be removed to the remaining structure, as it can lead to overstressing of the existing concrete. This can be avoided by shoring and propping the members to be repaired, and in some cases by partially removing loads from the structure or even by jacking. Ultimately, it may be needed a structural analysis that accounts for the transfer of loads from the concrete to be removed to the remaining structure. It is also important to ensure mechanical, rheological, and in some cases, aesthetic compatibility between the repair material and the remaining concrete. Since most of the shrinkage and creep of the existing concrete has already occurred, it is important to select a repair material with low shrinkage and low creep, so its mechanical contribution won't be compromised. As represented in this figure, when the repair material is subjected to shrinkage, it will be put into a tensile stress state and will only carry out compressive loads until the concrete of the substrate compresses accordingly. For an effective mechanical contribution of the repair material, it is also important that the models of elasticity of the repair material is similar to that of the existing concrete. This will avoid overstressing the one with the greatest models. For non-structural repairs, however, a lower model of elasticity of the repair material may be beneficial. For aesthetic compatibility, when required, it is recommended to prescribe trial testing to check compatibility of color, texture, and other visual characteristics. One of the most common problems in repairing is cracking and debonding of the repair material, mostly due to the drying shrinkage. To mitigate this risk, it is important to select materials with very low shrinkage, and also to prescribe a good preparation of the substrates and curing of the repair material. It is important to ensure that all the surfaces of the substrate are properly roughed in order to promote a good bonding with the repair material. It should also be prescribed, whenever possible, the full encapsulation of exposed bars with repair material by undercutting them. This can have several benefits, as it provides a better clearance for cleaning, enables the repassivation of steel bars, avoiding the development of corrosion in their back face, as already explained by my colleague, Sofia Ribeiro. It anchors the repair material to the substrate, preventing it from falling from the structure in case of detaching. It also provides a full circumference bonding between the bars and the repair material, which can be compromised if aggressive techniques such as stripping hammers are used to remove the concrete. In this regard, it is also highly recommended to prescribe trial testing to assess the tendency of the repair material for cracking. There is also the risk of incipient anode effect, which was already discussed in the previous session. Repair also usually involves filling narrow spaces with repair material. To ensure that there will not be such problems, the designer should specify a proper maximum aggregate size for the repair material, as well as recommend an adequate placement technique, which should be ultimately selected based on trial testing. Trial testing usually involves checking if the repair material completely fills all the spaces in the forms with the help of acrylic windows, coring, and also pull-off tests. There are also often restrictions on anchoring new reinforcement when needed to the existing structure. This can be done by several methods, such as by holes in the substrates with special mortar or resin, or it can be by connecting the new bars to the existing ones, or even using external anchoring devices when short anchorage lengths are required. It will now be described the main techniques used in the preparation of the substrates. First, we should remember the main steps involved in this preparation, which starts with the removal of the faulty concrete from the members, then roughening of the substrate, cleaning the substrate and the exposed reinforcing bars, and finally wetting of the substrate, which in case of an hydraulic repair material is to be used. Three main techniques are commonly used for preparing the substrate. The first one is called blasting, which consists of projecting an abrasive medium at high velocity against the concrete surface. Two of the most common blasting techniques are the shot blasting, which consists of mounted equipment with a blasting wheel that propels metal grains against horizontal surfaces, which are then vacuumed by the same equipment. The other is grit blasting, which consists of projecting other types of medium from a nozzle, such as sand, sodium bicarbonate, and dry ice. Water can also be added into the nozzle to reduce dust, which can be a problem, especially when using sand as a medium, as it may lead to health problems to the operator, such as silicosis. Blasting techniques are commonly used for cleaning and removing shallow depths of concrete, as well as for roughening the substrate. Although grit blasting is also very appropriate for cleaning exposed steel bars, as shown in this figure. The second technique is the water pressure technique, which consists of ejecting a stream of pressurized water from a nozzle at high velocity against the concrete. Different water pressures can be used depending on the stage of the preparation of the substrate. For removing small depths of concrete, roughening the substrate and cleaning steel bars, water pressure is usually not greater than 70 megapascal. For an efficient removal of concrete, much higher water pressures need to be used, and in that case, the technique is called hydrodemolition. Water pressure techniques are the most recommended for preparing the substrate, since they can be used in all stages and usually ensure a sound and well-roughed substrate. However, due to the runoff volume of water, they cannot be used in every situation. Here are some examples of this technique. We have a handheld equipment to remove a shallow depth of concrete in the beam. Then we have a simple nozzle to roughen the surface in underwater repair. We also have mounted automatic equipment, which can be very productive to remove concrete in large areas. Mechanical percussion techniques are also very common. They can be a handheld chipping hammers, which are frequently used. Different types of tips can be installed in the chipping hammer, such as a chisel, a pointer, a bush head, as the one in the figure. Large chipping hammers and jackhammers are also often used, although jackhammers are less recommended due to the end-arm vibration syndrome. Other techniques such as scaling, milling, and grinding can also be used for removing small depths of concrete and roughening the substrate in cases where the depth of removal does not reach the reinforcing bars. Mechanical percussion techniques can be very productive. However, they can also induce microcracking and partial spalling in the substrate, which may compromise bonding with the repair material. This type of damage should be assessed during execution, for example, by visual inspection of the substrate and by pull-off tests performed directly on the substrate or on experimental areas with repair material applied to the substrate. The damaged layer, usually up to about 10 millimeters deep, should be removed by a less aggressive technique such as blasting or water pressure cleaning. Ultimately, connectors may have to be installed in the substrate to ensure the monolithical behavior of the members to be repaired. Now we'll address the most common techniques for placing the repair material into the forms by briefly describing each one and pointing out their advantages. The most common consists of pouring the repair material into the forms by the action of gravity. It can be through openings in the forms or holes in the opposite face of the members to be repaired. Its main advantage is that it does not require special execution skills. Conventional concrete can be used, although there is a growing tendency for self-compacting concrete since it does not require vibration. The second technique is usually called form and pump and consists of pumping the repair material into the forms which is then pressurized after filling the cavity. This pressure forces the repair material to fill all the spaces and to consolidate, so no need for vibration. It also provides a good bonding with the substrate and ensures the full encapsulation of the reinforcing bars. This technique is particularly useful for overhead repairs, for the overhead repair of slabs when their upper surface is not accessible. The last technique is called pre-placed aggregate methods and consists of a two-step procedure. First, the coarse aggregates are placed into the forms during their installation. In a second step, a cement sand grout is injected to fill all the voids. The main advantage of this technique is the usually low shrinkage of the pre-placed aggregate concrete due to the continuous contact between the coarse aggregates before and after injecting the grout. This method can be also advantageous in repairs with highly congested bars or other hard-to-reach places, since the aggregates can be placed in those spaces during the installation of the formwork. Due to the large number of factors affecting the success of each placement technique here described, it is recommended to perform trial tests to check if they are appropriate to the repair conditions. As an example, it is here presented a case. It is here shown a case where the repair with pre-placed aggregate concrete was tested during an experimental block. In an experimental block, using formwork with acrylic window to check if the grout completely filled all the spaces. After hardening of the grout, cores were taken from the block to check the quality of the interface between the substrate and the repair material. Unfortunately, due to the large heterogeneity detected on that interface, as shown in the thick layer by the thick layer of grout on the interface in the picture on the right, it was decided to proceed with self-compacted concrete as the repair method. In conclusion, the casting place is a very versatile repair method. However, some aspects have to be properly addressed in both the design and execution stages, such as the need to ensure an effective transfer of loads between the repair material and the existing structured concrete, the risk of incomplete filling of all spaces with the repair material during execution, and the risk of cracking and debonding of the repair material after hardening. Due to the large factors affecting the success of this type of repair, trial testing is always highly recommended. That's it. Thank you.
Thank you, André, for your nice and clear presentation. Well, it seems that there are no questions. So, André Monteiro, thank you once again for your presentation.
Thank you.